afternoon, everyone. First of all, I'd like to thank the organizing committee for having me here and such a wonderful arrangement they have made for this conference. So as it is clear from the title of the presentation, I will be talking about the characterizing the plasma environment around the planetary and exoplanetary bodies. So if I say the planetary body, I will be talking about the planets in our solar system. And if I talk about the exoplanetary body, it's planets observed outside our solar system. So let me begin with, so basically I divided my presentation in two parts. In the first part, I will be mainly talking about analyzing the plasma environment around the planetary bodies. And let me begin with the first part of the presentation. So in this part of the presentation, I will be mainly talking about my work related to in situ spacecraft measurement and plasma simulation. So the work and result which I will be presenting in this talk is a part of the FP7 European project, which was funded by the European Union. And one of the objectives of the project was to have a better understanding in planetary magnetosity region. Okay, so first we need to understand what is magnetosity region here. So what you see here, these are just the artistic impression of two magnetospheres. On the right side, it is the Earth magnetosphere. To the left, you see the magnetosphere of the Venus. So you might be aware of that Earth has its own intrinsic magnetic field, but Venus does not have its own intrinsic magnetic field. So how does the Venus have the magnetosphere? What is the reason for having the magnetosphere? So basically, it is an induced magnetosphere we have around the Venus. So what happens in the case of Venus, the ultraviolet radiation which is coming from the sun ionizes the upper atmosphere of the planet and create the ionosphere. So this ionosphere deflects the incoming solar wind when the thermal pressure of the ionosphere exceeds the solar wind dynamic pressure and create a sort of magnetic barrier on top of the ionospheric obstacle and create a detached boson, which you can see here. Somehow it's not working. So this is the boson which you can see here. Yeah? So magnetosite is a region between these two boundaries, magnetopause and boson. So magnetosite is, you can say, a very unique natural laboratory where you can analyze plasma in a bounded region, something which you do in the laboratory plasma. Basically, the idea was to analyze the turbulence processes, what is happening in these two planetary bodies. And because this is the induced magnetosphere in case of the Venus, it is highly variable in terms of the solar cycle. So main idea was to characterize the turbulence processes under solar maximum and solar minimum condition. But the work which I will be showing here is, I have the events for the solar maximum as well, but here I will be only focusing on the events which we have observed in the solar minimum condition. Okay? So I use the magnetic field measurement using the magnetometer data on board the Venus Express and cluster. As you might be aware that Venus Express is a single spacecraft mission. However, the cluster is the constellation of 4 spacecraft. To have a comparative study between these two magnetized and unmagnetized body, I only consider cluster 1 data for have a better comparative study. So I use the magnetic field measurement provided by Venus Express magnetometer and cluster flux gate magnetometer. And then I have also the plasma parameter provided by Aspera and CIS on board Venus Express and cluster flux gate respectively. So I have selected only those events where I have the measurement for the magnetic field as well as for the plasma. For cluster, it is very easy to have because cluster, it is well documented measurement you have, but for the Venus, it is very hard to have at the same time, because for the Venus, we have the resolution of 3 minutes only. So sometimes you have the magnetic field measurement, but you don't have the plasma measurement. So that is a very hard part of having the event selection in case of the Venus. So I have the primary data, that is the magnetic field measurement provided by the magnetometer, and the secondary parameters are the ion movement data, that is the ion flow velocity, temperature, and density of the ions. Okay? So I started with identify the magnetosite even for the Venus. So here what you see, the identification of the Venus magnetosite. So I started with the analyzing just eye inspection on the magnetic field time series data provided by Venus Express. And what you see here, there is a sudden jump in the magnitude of the magnetic field, which shows the occurrence of interaction of solar wind with the planet ionized atmosphere and the boson crossing. And after that, you can see there is high amplitude magnetic field fluctuation. Then you can say, now you are inside the magnetic field because it is well compressed region because of the two boundaries available, are there. And then you select the time event in that region. But using this selection procedure, I was only able to select the event with maximum time length of 10 minutes. But we wanted to have a statistical investigation. Then we modified the selection procedure. Then we simultaneously scan the ion spectra, electron spectra, ion spectra, and we see the variation on the ion velocity, change in the number density, and change in the magnetic field fluctuation. So the transition from the solar wind to the magnetosphere is quite evidently observed as a heating in electron and ion spectra, which you can see here. So the temperature is much higher than the solar wind. And at the same location, you can see there is a high amplitude magnetic field fluctuation, and then you say, oh, now we are inside the magnetosphere, and you can select the event. So using this method, I was able to select more than, I think the time interval of the event was between 35 minutes to 1 hour, 60 minutes. And in total, I have selected more than 750 events in case of the Venus. For case of the Earth, I have selected only those events where the spacecraft remain in the day side, the magnetic field fluctuation amplitude is less than 70 nanotesla, and the ion velocity less than 450 kilometers per second, and the ion temperature more than 0.5 million Kelvin. So for the Earth magnetosphere, I have selected more than 330 magnetosphere events. Then magnetic field spectra, what you see, this is the superposed magnetic field spectra computed in the spacecraft frequency domain and also in the wave number domain. So to have the wave number magnetic field spectra, I used Taylor-Frozen hypothesis to map the frequency, spacecraft frequency, to the wave number. Okay, so on the top panel, you can see this is the superposed spectra for each of the selected event. So the magnetic field fluctuation in each event is normalized to the mean magnetic field, and the frequency and the wave number are normalized to characteristic temporal and spatial scale. That is the ion gyro frequency and ion gyro radius. And this black thick line which you see shows the median trend of the spectra. So spectra, we have the power law trend from low to high frequency side, and there is a slight dip at low frequency side, after which the spectra become steeper. So these two phenomena we have in the both planet, but the steepening in the spectra is happening at different scale. So what we have done to analyze closely how the spectral slope distribution is changing from low to high frequency side or from larger to smaller scale, we have developed an automatic numerical procedure. So in this automatic numerical procedure, we look for the power law frequency range, and then we estimated the spectral slope value in that frequency range. So what you see here, it is nothing, the 2D color-coded histogram showing the frequency is shown in terms of, in the unit of ion gyro frequency on the x-axis. The spectral slope distribution is shown on the y-axis, and the cumulative number of occurrence of different spectral slope values are shown with the color bars in it. So these top panels are for the Venus, the bottom panels are for the Earth. The left panels are in the frequency domain, the right panels are in the wave number domain. And what we have observed, that in case of the Venus, there is continuous change in the spectral slope value from large to smaller scale. So spectral slope value is decreasing from low frequency to high frequency side. In case of the Venus, if you see the left top panel. However, if you see the Earth magnetosphere, there is a sudden change in the spectral slope value from low to high frequency side. Okay? And similar kind of feature we have observed in the wave number domain. And we have observed there is a spectral break at this point, which is close to iron gyro radius in case of the Venus. And the spectral break in case of the Earth is observed at this position, after which we have the steeper spectra. So as you might be aware of, this kind of turbulence spectra may be attributed by the waves, or turbulent, it can itself also give some sort of hint about existence of possible wave mode that is there in the magnetosith region, which could be reason for this kind of steepening which you observed in the magnetosith region. So we did some additional analysis. So on top of the magnetic field turbulence spectra, we also computed the propagation angle. The propagation angle is nothing, it is the angle between the wave vector and mean magnetic field. And we have also computed the compressibility. The compressibility is the power in the compressible component of the magnetic field divided by total power. So in the left panel, what you see is the propagation angle. So at low frequency side, what you see, the propagation angle is quasi-perpendicular to 90 degree, because what you see here, it is ranging between 70 to 90 degree in this frequency range. In the middle frequency range, it has a broader spectrum. In most of the cases, it is quasi-parallel to the mean magnetic field, and there are some event which is quasi-perpendicular to the mean magnetic field. So this is for the Venus. Again, if you go to the high frequency side, what you observe, it is quasi-perpendicular to the mean magnetic field. The theta kb is ranging between 70 to 80 degree. Now, if you see in case of the Earth magnetosith, it is predominantly 90 degree to the mean magnetic field at low frequency. In the middle frequency range, it's quasi-parallel to the mean magnetic field, and if you go to the higher frequency range, again, it is close to quasi-perpendicular, 70 to 90 degree. But if you go beyond this frequency range, this behavior is gradually vanishing. Now, if you see the right panels, this shows compressibility. So compressibility has a wide range of variation at low frequency, ranging between 0.1 to 0.9. In the low frequency range, it is close to 0.1 or 0.4. And if you go to high frequency side, again, it is ranging between 0.2 to 0.5. So what we have observed, a different spectral slope at scale smaller or larger than the iron gyro radius, or you can say at low and high frequency side. In most of the cases, we have not seen Kolmogorov scaling in case of the Earth magnetosith, which you usually see in the solar wind. However, it was evidently observed in the case of Venus. Then the power law is consistent at least for the at least one decade of the frequency. If you see the spectra, you can see that. And the spectral break was observed close to iron gyro radius. The most important point which we have observed, that a low frequency propagation angle is at low frequency, the propagation angle is quasi-perpendicular to the mean magnetic field, and compressibility shows the mixed distribution, highly compressible to incompressible. As you might be aware of mirror mode structure, which is highly compressible linear structure, and the wave vector angle of propagation can change to the 90 degree, around 90 degree. And if you talk about the iron cyclotron wave, it is highly incompressible, circularly or elliptically polarized waves, and angle of propagation is parallel or quasi-perpendicular to mean magnetic field, between 70 to 80 degree. If you go beyond, it will become the kinetic Alfvén wave. So if anyone is interested to seeing what kind of waves are there, you should focus on these wave modes, if you are talking about the magnetosith region. Now I'd like to discuss about plasma environment around the exoplanet. So I will discuss about the multi-fluid code which we have developed in our house. Okay? So this is the multi-fluid code which is capable of analyzing different sort of exoplanet. With this multi-fluid code, we are able to analyze hot Jupiter kind of exoplanet, warm Neptune, super Earth, but so far we have not analyzed any terrestrial kind of exoplanet. There is a limitation for the such kind of multi-fluid code as well. So within this code, we have considered that we have taken the hydrogen-dominated atmosphere. So mostly we have considered the hydrogen atoms, molecules, ions as an atmosphere there are heavy species also included within the code, but those species are included as a separate entities. Then we have also considered thermal and non-thermal mass loss of the atmosphere as well. We also have the photochemistry block within the code. So we have included the basic photoionization and photochemistry within that block. Some of results are already published, but here I will only discuss about a particular exoplanet, that is WASP-12b, which you can see at very right. So basically WASP-12b was detected using the first detected with the optical photometric. So that is the ground-based measurement it was there. So it has a mass of about 1.4 mass of Jupiter, radius about 1.8 radius of Jupiter. So it was first observed by Hebb et al. In 2009. And the basic way to detect the planet is transit method. So what you see here, planet orbiting around its host star, and when it passes in front of the observer and host star, there is a slight blockage of the light which is coming to the observer. And you can see there is a dip in the light curve, and this way you can detect the exoplanet. That is one method. Most of the exoplanets now are detected using this transit method. So the detection of exoplanet was started early 90s. And until 2000, it was only few exoplanets detected, but with the help of transit method, we now have more than 5,000 exoplanets detected and confirmed. So this exoplanet WASP-12b was again detected in near ultraviolet using the cosmic origin spectrograph onboard Hubble Space Telescope. What special features they observed in this near ultraviolet observation? The transit has started much earlier than the optical, 50 minutes earlier than the optical. So this they call early ingress. So it started 50 minutes earlier. However, the egress is at the same location like the optical one. So there are two leading hypotheses trying to give the reason behind why they have observed this early ingress phenomena in case of WASP-12b. The first explanation is based on the fact that the planet is too close to its host star. Its upper atmosphere is mostly ionized. It loses its atmosphere to the star and forming accretion disk around the star. That's why you get this early ingress. So there is a optically thick material ahead of the planet. That's why you get this early ingress phenomena. The second explanation is based on the fact that the planet is orbiting with a supersonic velocity in the stellar wind and creating a sort of bow-shock ahead of the planet. And that's why you see this early ingress phenomena. So with this multi-fluid model, we are trying to analyze these two hypotheses. So we started with the 2D model, 2D multi-fluid model. So what you see here, we have taken the cylindrical geometry. So consider the symmetry of the geometry. We have only modeled the half part of the simulation box. What you see, the planet is sitting at the center of the geometry. The star is sitting on the top of this. And we have run different set of simulation depending on the XUV radiation. So we started with the solar type XUV radiation. Then we have considered 2 times solar type XUV radiation, and then the 4 type XUV radiation. What you see, this is solar type XUV radiation. It is showing the density distribution of the atoms, protons of planetary and stellar origin for XUV5. Then we have XUV10. Then we have XUV20. And what we see that even the fast and dense stellar wind is not able to stop the expansion of planetary wind. It's expand beyond the Rose lobe and moving towards the star. However, the stellar wind dynamic pressures compresses the flow of this and form a kind of lateral ionopause boundary here. So most of the atoms flow inside this boundary. So in this first simulation, we have included all the physics, even the tidal force of the star. But we were not able to see the formation of bow shock. which could be the reason for the early ingress. Then we tried to see whether we can have the Bosock formation. We tested a less realistic case. We have excluded the Coriolis force. We have also excluded the tidal force. But with the less realistic case, we were able to see the formation of Bosock, you can see here, even though there is no magnetic field. Fine, I will be. But in both cases, we are not able to see the phenomena of early ingress. We also computed the mass loss rate of the atmosphere, which is losing because of heating and XUV radiation. But that I'm not showing here. So basically, in both cases, we are not able to see the phenomena of early ingress. And one of the reasons for this is that we are trying to realize a three-dimensional problem with a 2D model. So far, we have done this with the 2D model. Then we upgraded the code to 3D model. So now what you see, it is the whole system. The star is sitting here. The planet with the extended atmosphere is sitting here. And the flow of different species are shown with the streamlines. Okay? The top bar shows the velocity of the protons. Protons, if I talk about the protons from the planetary and stellar origin. And the bottom panel shows the density of the protons. And this is one of the many simulation run. This is for XUV5, so solar type XUV radiation. Very fast stellar wind and over-dense stellar wind condition. But with this, what you see, we are able to see the formation of Bosock. That is not very aligned with the star. So planet is sitting at the center of this box. The planet is here, the star is here, but it is at the angle 45 degree to planet-star line. And this is nothing just the density distribution of different components. So what you see, the planet is at this location. We are seeing the density distribution at the 45 degree between planet-star line. What we have observed, the magnesium doublet line, the density of the magnesium doublet line is drastically changing after 2 or 3 planetary radii. So hardly there is any magnesium left after 2 to 3 planetary radii. Then we have simulated the transit light curves. So what you see here, these are the simulated transit light curves. We have taken different sort of parameters. Stellar wind parameter, we have also taken different XUV radiation. So we have the XUV, solar type XUV radiation, then the twice the solar type XUV radiation, then the 4 times XUV radiation. We have also considered different velocity of the stellar wind. We have taken the fast and slow stellar wind. We have considered rarefied stellar wind condition, dense, moderate stellar wind condition, dense and over-dense stellar wind condition. So in total, I have run more than 100 simulation runs. But here I am showing just few of them. So what we have seen, we simulated the transit light curve. We compared with the optical one. The top one is the optical one. And these, the black circle and the red triangles, are from the near ultraviolet measurement. And what we have observed, we have seen this early ingress. So you can see it is starting much earlier than the optical. But what is the problem we are facing in this simulation also? Our egress is also delayed. So this is the major problem we are having with. But so far, this is more hydrodynamic model. We have not included magnetic field in it. So this we are looking forward to include in the simulation box so that we can see the real picture what is happening. But so far with this model, we are able to see the phenomena of early ingress, and it is matching quite well with the near ultraviolet observation as well. Because if you see the error in the measurement, it is fitting well with the measurement as well. So with this, thank you for your patience. So if anyone has any question, I'd like to take it.
Thank you, Dr. Dwivedi. Question? Yeah.
Well, thank you for this nice two-part talk. My questions are related to the first part of your talk.
Yes.
There are two questions. The first is a question, second is a comment.
Yeah.
The first one is that when you talk about the turbulence in the magnetostate region,
Yes.
you say that for the art case, it is non-Kolmogorov kind of things.
Yes.
In the Venus, it is a Kolmogorov.
Yes.
In interstellar matter, it seems like a Kolmogorov.
Yes.
So what might be the reason for that?
Not having the Kolmogorov scaling in the Earth magnetosid.
Yes.
So it is quite obvious because mostly it is, when you see the Venus, let me go to the, so when you see, in case of Venus, what happens, this bosoc is highly variable. It is the induced bosoc, yeah? Okay. So mostly whatever the feature you see in the solar wind, that is present in the magnetosid region. However, in case of the Earth magnetosid, because it is well protected, well here,
Right.
you don't see the same feature which you usually observe in the solar wind.
Okay.
So this non-detection of Kolmogorov is also, I think many people have already published it. That is there also.
That's okay.
So far we have not, I think I have published only some part of it. We have not published this comparative study so far.
Okay.
But yeah,
Well, the second part is that when you talk about the mirror mode oscillations,
sorry?
mirror mode oscillations, mirror mode.
Yes,
There is a 2004 geophysical research later paper
yes.
where it has been contested these are not actually mirror mode, but these are slow mode solitons. Is there any kind of, are you aware of that?
Regarding which part of, I mean, because in the Earth magnetosid, it has been observed in many times. I can share many of the papers. They have detected this mirror mode structure within the magnetosid region of the Earth. I'm not sure about the Venus, because in Venus, it is mostly ion cyclotron wave they have observed.
Okay.
But for Earth, they have already observed the mirror mode structure, which is not a wave. It's just a structure.
Okay.
Yeah.
Okay, that's fine.
Bhargav? Bhargav? Anyone from student? Any question from student? Bhargav, go ahead.
Yeah, very, very impressive talk, I would say. I have a question with regards to the second part of your talk.
Yes.
When you're talking about this early ingress and so on. The first question I have is, do you actually also include, you said you include FQV, flux and so on, but do you also include the fact that the stars would be flaring at certain stage and you have certain large chunk of X-rays coming over there?
So you're talking about whether I have included the evolution of the star.
Yes.
Not so far, because the limitation with such kind of modeling is that you rely whatever the best thing you have so far. So far we are using solar type XUV radiation and same solar wind model, because we don't have such kind of measurement for such kind of exoplanet. That is the limitation we are facing. If you have more measurement, you can think about those things also. Yeah.
I understand that the simulations are extremely expensive and so on.
Yes.
So, but regarding the early ingress and the out part, which is almost symmetric,
Yes.
have you considered doing more sort of resolution study runs where the ingress and the outgress basically are kind of more compressed because more cells you would resolve the bow shocks in?
That is the way. Another thing which is missing in this code, that is the magnetic field. Okay. That is also important, because it's not only the planet magnetic field, also the stellar magnetic field which you need to consider. And I think this is the limitation of this multi-fluid code as well, because you are modeling a system which is highly dependent on the magnetic field also. So that is, but this is true. We have not so far included what you are suggesting, but we are looking forward to do that. Yeah.
Thank you. Thank you.
you.
All the best.
A quick question. So you didn't mention about the slopes. Basically, you said one is less steep, another is steeper. So what are the slopes you are getting? Are they really random, or because you are saying non-Kolmogorovian?
So that's what I like to mention here. So basically, when you see, most of the time what you see, in most of the paper what they see, they give you the average value of the spectral slope. Yeah? But what happened when you plot this power spectral density, sometimes the fluctuation is going high and down, and also the precise, because this is what we have done in this automatic numerical procedure. We have measured the spectral slope distribution in a sliding window segment. So there is an overlap between the sliding window, and then we have moved from the low to high frequency side so that you have more precise measurement. And each of these bins are normalized by the event. So this is more precise measurement how the spectral slope value is changing, because this point is very important.
Yes.
Whether which location you are getting the spectral break. And sometimes when you have this average spectrals of distribution, that point is missing. Yes.
Yeah, one question there.
I am John from IIT Hyderabad. So thank you for very nice talk. So my question is about in magnetometer sheets you were saying that the different compressibility in different frequency range.
Yes.
So you are also mentioning that these spectra could be due to the Einstein-cyclotron waves.
That is just a sort of hint. I have not done the wave analysis. I just gave some sort of hint so that anyone who is wave mode, they can look for these kind of wave mode. Okay? But if you want to have the wave analysis, that is separate. Another point which you are missing, in this event selection, I have not categorized whether it is quasi-parallel or quasi-perpendicular events. That also highly influence the turbulence inside the magnetosheet.
Okay. So could it be like these are due to the mix of some Einstein-cyclotron wave and kinetic alpha wave, like that kind of, because you are getting different compressibility at different frequencies?
Yeah, definitely, it could be. But then you have to do the wave analysis as well, which I have not done so far. Okay?
Thank you.
Thank you.
More from student? No? If not, then let's thank Dr. Dwivedi again.